Example 12.7. Compressive stress in a pillar. A sculpture weighing 10,000 Newton rests on a horizontal surface at the top of a 6.0 meter tall vertical pillar, figure 12.19. The pillar's cross-sectional area is 0.20 meters squared, and it is made of granite with a mass density of 2,700 kg per meter cube. Find the compressive stress at the cross-section located 3.0 meter below the top of the pillar and the value of the compressive strain of the top 3.0 meter segment of the pillar. So first, we find the weight of the 3.0 meter long top section of the pillar. The normal force that acts on the cross-section located 3.0 meter down from the top is the sum of the pillar's weight and the sculpture's weight. So once we have the normal force, we use the equation 12.34, which is the tensile stress equals deforming force over area of an object to find the stress. So to find the compressive strain, we find the value of Young's modulus for granite in table 12.1 and invert equation 12.36, which is y equals tensile stress divided by tensile strain. Solution. First, we will find the volume of the pillar segment with height 3.0 meter and cross-sectional area equals 0.20 meter cube. Therefore, pangitaon sa nato una ang volume sa pillar segment, which is we will derive to the formula area of an object or a cross-sectional area times the height. So therefore, the area is equivalent to 0.20 meter cube multiplied by 3.0 meter, which is the height, is equal to 0.6 meter cube or 0.60 meter cube. So therefore, the volume of the pillar segment is equal to 0.6 meter cube. So given the density of granite, 2.7 times 10 cube kilogram per meter cube, we will find the mass of the pillar segment, which is mass equals to density times the volume, which is the density is equal to 2.7 times 10 cube kilogram per meter cube multiplied by the volume 0.6 meter cube is equal to 1.62 times 10 cube kilogram. Therefore, the mass of the pillar segment is equal to 1.62 times 10 cube kilogram. After that, we will find the weight of the pillar segment, which is equal to mass times gravity. So, the given mass is 1.62 times 10 cube kilogram. The monetong gipangita before this equation. So, multiplied by the gravity 9.80 meter per second square. So 1.62 times 10 cube kilogram multiplied by 9.80 meter per second square is equal to 1.59 times 10 to the power of 4 kilogram meter per second square is equivalent to 1.59 times 10 to the power of 4 Newton. Therefore, the weight of the pillar segment is equal to 1.59 times 10 to the power of 4 Newton. So, the weight of the sculpture is equal to 1.0 times 10 to the power of 4 Newton. So, the normal force on the cross-sectional surface located 3.0 meter below the sculpture is we will use this formula. So, para makita nato ang normal force nga sa cross-sectional surface located 3.0 meter below the sculpture is deforming force is equal to the weight of the pillar segment plus the weight of the sculpture, which is the weight of the pillar segment is equal to 1.59 times 10 to the power of 4 Newton plus the weight of the sculpture, which is the 1.0 times 10 to the power of 4 Newton. We will add the both of them. So 1.59 times 10 to the power of 4 Newton plus 1.0 times 10 to the power of 4 Newton is equal to 2.59 times 10 to the power of 4 Newton. So we will solve for the stress. After that, after those equations nga atong naagian, isolve na nato ang stress, which is ang gipangita. So stress is equal to deforming force divided by the cross-sectional area. So, Deforming force is equal to 2.59 times 10 to the power of 4 Newton divided by this cross-sectional area 0.20 meter squared. So divide them and we will get the answer 129,500 PA equals therefore ato siyang transform. So 1.29.5 kPa. So after that, we will find the strain. So the Young modulus for granite is equal to 4.5 times 10 to the power of 10 Pa is equal to 4.5 times 10 to the power of 7 kPa. Therefore, the compressive strain at this position is equal to strain equal to stress over the Young modulus for granite is equal to 129.5 kPa is equal to 4.5 divided by 4.5 times 10 to the power of 7 kPa. Therefore, come up ta sa answer nga 0.0028777778. In short, 2.88 times 10 to the power of negative 3. So, the normal force acting on the pillar's cross-sectional area is not constant along its length, but varies from its smallest value at the top to its greatest value at the bottom. As a result, if the pillar has a constant cross-sectional area along its length, the stress is greatest at the base. Example 12.8. Stretching a rod. A 2.0 meter long steel rod has a cross-sectional area of 0.30 centimeters square. The rod is a part of a vertical support that holds a heavy 550 kilogram platform that hangs attached to the rod's lower end. Ignoring the weight of the rod, what is the tensile stress in the rod and the elongation of the rod under the stress? So, first, we compute the tensile stress in the rod under the weight of the platform in accordance with equation 12.34, which is tensile stress equals deforming force divided by the cross-sectional area. Then we invert equation 12.36, which is the y equals tensile stress divided by tensile strain, to find the rod's elongation using the original length equals 2.0 meter from table 12.1. Young's modulus for steel is y equals 2.0 times 10 to the power of 11 Pa. Solution. We will substitute the numerical values into the equation gives us. So stress equals deforming force divided by the cross-sectional area is equal to 550 kg multiplied by 9.8 meter per second squared divided by 3.0 times 10 to the power of negative 5 meters squared is equal to 5,390 kg meter per second squared divided by 0.00003 meter squared is equal to 1.8 times 10 to the power of 8 Pa. So after that, we will invert to the equation 12.36, y equals tensile stress. So delta L is equal to stress divided by tensile strain, which is the deforming stress is deforming over or divided by cross-sectional area, multiplied by the original length divided by the Young modulus for steel. So 1.8 times 10 to the power of 8 Pa multiplied by 2.0 meter divided by 2.0 times 10 to the power of 11 Pa is equal to 1.8 times 10 to the power of negative 3 meter. So after that, we will convert into millimeter. So 1.8 times 10 to the power of negative 3 is equal to 1.8 millimeter. Similarly to the column example, the tensile stress in this example is not uniform along the length of the rod. However, Unlike in the previous example, when the weight of the rod is considered, the stress is the rod is greatest at the top and lowest at the bottom of the rod where the equipment is attached. Example 12.9 Hydraulic Press. In a hydraulic press, figure 12.23, a 250-liter volume of oil is subjected to a 2,300 psi pressure increase. If the compressibility of oil is 2.0 times 10 to the power of negative 5 per atm, find the bulk strain and the absolute decrease in the volume of oil when the press is operating. According to the figure 12.23, in a hydraulic press, when a small piston is placed downward, the pressure in the oil is transmitted throughout the oil to the large position, causing the large piston to move upward. A small force applied to a small piston causes a large pressing force, which the large piston exerts on an object that is either lifted or squeezed. The device acts as a mechanical lever. So, we must invert equation 12.40, which is equivalent to K equals 1 over B equals negative delta volume over the original volume divided by delta density. To find the bulk strain, first we convert the pressure increases from PSI to ATM, which is delta density equals 2,300 psi equals to 2,300 divided by 14.7 atm is equal to 160 atm, and identify the original volume equals 250 liter. Solution. Substituting values into the equation, we have bulk strain equals delta volume over the original volume is equal to delta density over dB. So equals K delta density is equal to 2.0 times 10 to the power of negative 5 per atm multiplied by 160 atm is equal to 0.0032, and the answer is delta V equals 0.0032. The original volume is equal to 0.0032 multiplied by 250 liter is equal to 0.78 liter. Because water has a compressibility 2.32 times greater than oil, if the working substance in this problem's hydraulic press were changed to water, the bulk strain and volume change would be 2.32 times greater. Example 12.10 An old bookshelf. A cleaning person tries to move a heavy old bookcase in a carpeted floor by pushing tangentially on the surface of the very top shelf. However, the only noticeable effect of this effort is similar to the scene in figure 12.24, and it disappears when the person stops pushing. The bookcase is 180.0 cm tall and 90.0 cm wide, with four 30.0 cm deep shelves, all partially loaded with books. The total weight of the bookcase and books is 600.0 Newton. If the person gives the top shelf 50.0 Newton push that displaces the top shelf horizontally by 15.0 centimeter relative to the motionless bottom shelf, find the shear modulus of the bookcase. So, according to figure 12.24, an object under shear stress, two antiparallel forces of equal magnitude are applied tangentially to opposite parallel surface of an object. The dashed line contour depicts the resulting deformation. There is no change in the direction transverse to the acting forces, and the transverse length, or the original length, is unaffected. Shear deformation is characterized by a gradual shift, delta x of layers, in the direction tangent to the forces. So, the only pieces of relevant information are the physical dimensions of the bookcase, the value of the tangential force, and the displacement this force causes. We identify F equals 50.0 Newton, delta x equals 15.0 centimeter, and the original length equals 180.0 centimeter. And the area is equal to 30.0 centimeter multiplied by 90.0 centimeter is equivalent to 2700.0 centimeter squared. And we use equation 12.43 to compute the shear modulus, which is shear modulus equals shear stress over or divided by shear strain, which is shear strain is equal to delta x divided by the original length, and the shear stress is equal to the magnitude over the or divided by the cross-sectional area or the area. Substituting numbers into the equations, we obtain for the shear modulus. So shear modulus equals to magnitude divided by the area multiplied by the original length over delta x is equal to 50.0 n or Newton divided by 2700.0 centimeter squared multiplied by 180.0 centimeter divided by 15.0 centimeter is equal to 2.2 Newton over 9 centimeter square is equal to 2 over 9 times 10 to the power of 4 Newton per meter square is equal to 20 divided by 9 times 10 to the power of 3 PA is equivalent to 2.222 kPa. We can also find shear stress and strain respectively. 50.0 N divided by 2700.0 centimeter squared is equal to 5 over 27 kPa is equal to 185.2 PA. So, again, the shear stress is equal to delta x divided by the original length, 15.0 centimeter divided by 180.0 centimeter is equal to 1 over 12 divide is equal to 0.083. So, if the person in this example gave the shelf a healthy push, it might happen that the inducted shear would collapse it to a pile of rubbish. Much the same shear mechanism is responsible for failures of earth-filled dams and levees, and in general for landslides. Example 15.2. Determining the equations of motion for a block and a spring. A 2.00 kilogram block is placed in a frictionless surface. A spring with a force constant of K equals 32.00 Newton per meter is attached to the block, and the opposite end of the spring is attached to the wall. The spring can be compressed or extended. The equilibrium position is marked as x equals 0.00 meter. Work is done on the block, pulling it out to x equals plus 0.02 meter. The block is released from rest and oscillates between x equals positive 0.02 meter and x equals negative 0.02 meter. The period of the motion is 1.57 seconds. Determine the equations of motion. We first find the angular frequency. The phase shift is 0. Because the block is released from the rest at x equals a equals positive 0.02 meter, once the angular frequency is found, we can determine the maximum velocity and maximum acceleration. The angular frequency can be found and used to find the maximum velocity and maximum acceleration. So, angular frequency equals 2 pi divided by 1.57 seconds is equal to 4.00 seconds to the negative 1. So, volume max equals area times the angular frequency equals 0.02 meter times 4.00 seconds to the power of negative 1 is equal to 0.08 meter per second. So the A max equals to A to the angular frequency squared equals to 0.02 meter times 4.00 seconds to the negative 1 squared is equal to 0.08 0.32 meter per second squared. So all that is left is to fill in the equations of motion. So x of t is equal to a cos, open parenthesis, the angular frequency times time plus the phase shift is equal to 0.02 meter times cos times 4.00 s to negative power of 1 times t. So v of t is equal to negative v max sine, open parenthesis, the angular frequency times time plus the phase shift is equal to negative 0.08 meter per second sine 4.00 second to the power of negative 1 times t. And lastly, a of t equals negative acceleration max cos, open parenthesis, angular frequency times time plus the phase shift equals negative 0.32 meter per second squared cos 4.00 second to the power of negative 1 times t. So the position, velocity, and acceleration can be found for any time. It is important to remember that when using these equations, your calculator must be in radians mode.